Greetings everyone. Today I am going to present my cryptography project on the topic hash functions and zero knowledge proofs. So let's start with hash functions. So what are hash functions? Hash functions are specialized algorithms that convert a specific plain text into a hash value. So the plain text can be anything. So for example, you can have a PDF, a video, a 500-page novel or an entire database. Then we have a hash function which makes this possible, and this hash value is the fingerprint of the plain text. So the hash value is the fingerprint of the plain text, that is, it is specific for the specific plain text and is crucial for the transmission of the plain text. So instead of the plain text, we can just transfer the hash value to confirm the identity. It is difficult to reverse engineer or to receive the plain text PT again from the hash value. So it's like if you make a smoothie out of some fruits or vegetables, it is very hard to get, it is impossible to get the fruits back from the smoothie. So now let's see what are the possible uses of hash functions. So we have data integrity verifications, digital signatures, and password storage as the major uses. Other uses are link and chaining data. This is important, and anonymity and pseudonymity schemes. We will see the uses in detail as examples. Now let's see how hash functions are constructed. So if I have a hash function, if I have a bit length this and I apply a hash function on this, then what are the steps that take place on the plain text? So first of all, the plain text is divided into fixed blocks of, let's say, for our example, let's consider 2. So we convert the plain text into fixed blocks of 3 letters. Okay. Now we pad the plain text. So we have 7 letters here, 7 bits here, 1 and 0. Now we pad the plain text. So we have to convert it into a multiple of 3 because our block size is 3. So we have 9. So now to pad to the starting of the bit size, we add 1 followed by the number of zeros required. So here we require only 1 0. So we add the 0 and get our padded function padded bit as this. Now we apply compression functions on this. So first of all, to start, we apply the initialization vector, which is a publicly known fixed value, which is used first to compress this function. Then consequently, we apply the compression function over the new hash value obtained over each iteration. The compression function consists of functions such as AND, OR, XOR, and NOT, and other one is ROT. So if we have ROT in, then we remove the last n values from the bit size. So we have ROT 3, then for this we remove the last 3 values of this and add them to the starting. So we have in the reverse direction, which is ultimately the forward direction. So now let's focus on some of the properties of hash functions. First of them is that hash functions are one way. As we have already seen, if I have hash of m equals h, I cannot compute m from the h such that h of m equals h. So this is resistance against a first pre-image attack. So I am trying to find m from the hash value I have and the hash function. This is hard to do for a hash function. Next we have determinacy. Determinacy of a hash function tells us that regardless of the input, how many times I enter the same input, so I have h of m equals lowercase h. Now if I again inputs the same value, I get the same hash value h. Why is this important? this is important because if I receive different hash values for each iteration I do, then I will not be able to, for example, verify my password, which we will see in in the later part. Next, we have the avalanche effect that states that a tiny change in the plain text value has a drastically different hash value. So we will see a short video that I have made for the same. But for now, if I have a plain text hello and another one hello with lowercase h, then the hash of hello should have at least half of the bits different from that of the hash of the small case h hello. Now we also have resistance against the second pre-image attack or collision resistance. So second pre-image attack resistance is that it is computationally infeasible for me to find two different plain texts M1 and M2 such that the hash of both of them is same. So this is important because if I am able to produce another hash for the same another plain text that has the same hash, then I can possibly manipulate the user by helping them install a malicious file instead. Now let's move on to the history of hash functions. Some basic hash functions, the type of hash functions we had, were simple checksums and cyclic redundancy checks. Cyclic redundancy checks are still even used today in Ethernet, Wi-Fi, and such connections, but they were generally used before. For simple checksums, if I have a string of bits like this, then we just add the bits. So we have 4 here, and take the mod of a random number. So for example, let's say 256 here, to get the checksum 4 in this case. For cyclic redundancy checks, we have for example, for this value, we have the cyclic redundancy check, as we can uh, repeatedly apply the polynomial division over a field, let's say f16 or f32. So we have CRCs in generally 16 and F16 and F32 only, to result in the cyclic redundancy sum, which we can use to verify the data. These are not one way, and it is easy for us to generate collisions in them, and they also lack the avalanche effect. Now, as for MD5 and SHA1, predecessors of the current SHA 256 and 512, we have MD5 produced a 128-bit hash. So we had 4 processors for them, and when I enter one to any bit, then it is converted into chunks of 128, sorry, and then each chunk of 32 is entered into the corresponding bit register. We have 4 bit registers here in the processor, and 62 or 64 rounds of the compression function is applied. So one round is with the initialization vector IV, and the other 63 rounds are with the hash value obtained by applying the first initial. So we have compression function on A results in A dash, then we have compression function of A dash on A dash results in A dash dash. Now, for in the case of SHA1, all the values change. So we have, they improve the efficiency as well. So we have 80 rounds instead of 64, and 5 processing units, with each with 32-bit constant, that's same, and so total we have a 160-bit hash value. Now, a collision attack by Steven Sattel in 2017, previously by some Chinese scientists in 2014, calculated the differential characteristic for this, and they broke the SHA1. MD5 was also broken by the same method. But for the SHA one, they analyzed two plain texts such that hash of both of them is the same. So hash of A dash and the hash of A both is X. So now they can calculate delta A or the differential characteristic as A or A dash, and after meticulously analyzing the different inputs, they found out the differential characteristic of the equation and the chosen suffixes and prefixes which you can add to the same plain text either in front or in the back to result in the same hash value. Now let's come on to the pigeonhole principle. So if we have four pigeons here and three holes here, so this is the input space and this is the output space. Since the input space is greater than the output space, at least some variables, some in the input space are left out. So this can go here. This one is left out in this case, for example. Now, how this connects to our hash value is that if in the hash values I have infinite number of inputs, so my input space is infinite and my output space is limited to, for example, 2 is to 256 for SHA to SHA 256. Now, this by pigeonhole principle, we have that at least two different plain texts produce the same hash. So this is not hard to see because infinity is greater than 2 is to 256. But it is nothing to fear much about because 256, just to give an idea of the number 256, um, it is much greater than the age of the universe itself if taken in seconds as well. Now, another important thing is the birthday paradox. What the birthday paradox states is that, so first of all, you can pause the video and try this question on your own. Okay, so you will receive an answer as to 23. So 23 you may feel is too small, but yeah, that's true because if you have 23 people, then the number of possible pairs you have is 23 into 22 by 2, which is 253. So 253 is the number of the total possible pairs. Now with this you can calculate that what is the probability of obtaining two people with not the same birthday and subtract that from 1 to result in the number which is greater than 50, that is about 51 to 52%. Now when you repeat this procedure with a group with 70 people, you get a value greater than 99%. So what does this indicate is that you need to potentially try a smaller amount of plain text that you may think necessary in order to get the hash value or the hash function itself. Now let's focus on SHA 256. It was a part of the SHA 2 family designed by the NSA itself, and it produces a 256-bit output with 64 rounds of computation. We have already seen it. These all are the same, the definition and terms are same as well. The difference is that we use different initialization vectors, different padding, and uh, the values are just different. So now let's move to the next topic. Here we have a demonstration of the avalanche effect in hash functions. So here we have the first plain text, that is hello world, with h in uppercase, and we have the hash value as this. So now when we have the hello world same with lowercase h, we see that the hash value is drastically different. So if you remember the first value, this one, then you can identify that the second hash value that we get is totally different. This indicates the avalanche effect in hash functions. Now, talking about the potential attacks on SHA-256, we have brute force attacks that are generally ineffective against SHA due to the vast input space and vast output space, which makes it computationally infeasible. For dictionary attacks, we have the hackers calculate the uh, hashes for potential plain texts with high probability and then calculate the differential characteristic for different plain texts, hashes of different plain texts in in order to receive the hash function. Rainbow tables, on the other hand, are sophisticated types of dictionary attacks in which the hackers use the same function as dictionary attacks, but they apply a reduction function R, where reduction function is a possible inversion of the hash value. So reduction function is not absolute, but it's just a random function which may or may not result in the correct plain text. So hash function on x results in a value y, then they reduce the value y to result in another value x, then again they encrypt it, they hash it to receive another value a, and then this continues. Now when they have a leaked or compromised password, what they do is that they calculate the hash of that password, for example as the hash of password, and then match it to the hashes that they have calculated in the list. So this makes it drastically easier and simpler to calculate potential hashes for the plain text. Now let's see some real life and relatable examples. First we have file integrity or file storage. So if we have Alice and Bob, so Alice has a file A and she sends it to Bob. We have Eve, the adversary, with another file, lowercase a, and she intercepts the message and Bob receives E. Now we need to figure out if E is equal to A or E is equal to small case a. For this, we have first of all, Alice and first of all, Alice computes the hash of A and Bob computes the hash of E. It is simple. So if hash of A equals to the hash of E, then that's the same file that Alice had sent to Bob. If not, then Bob has received the tampered file. In password storage and safety, we also have the same concept. If I have a website and someone tries to log in into the website, they when they enter the potential the password, what I receive is just the hash of the password. So if they enter the password P, I receive the hash of P. But what I store is also the hash of P. That is because for security concerns, if my website is affected, then the users should not suffer. That's why I just calculate the hash of P and store it, not the password itself. And then the hash of P that the user enters P only, but the hash of P is the calculated one, and hash of P is tallied with the hash of P dash that I already have. If they come out to be same, then I grant the access, otherwise no. So that's all about hash functions. Now let's move on to zero knowledge proofs. So now let's move on to zero knowledge proofs. I will try to complete it in short due to the time constraint, but it's very interesting. So in zero knowledge proofs, a prover tries to convince the verifier. So we have a prover and a verifier. So the prover knows the information and the verifier does not know the information. So the prover has to convey the information to that, just that the prover knows that information, nothing other than that. But the verifier should be convinced that the prover knows the information. Without actually transferring any part of the information itself, such as uh, the encrypted function or the hash, nothing like that. So now we have a demonstration. So for example, I am the verifier and I am colorblind. So I show the prover two balls, just a simple demonstration. Now he tells me that this one is yellow and this is pink. Now I swap the balls, or I do not, and I show them again. So I personally just know that I have swapped them or not. Now again he chooses which one is pink and which is yellow. Now again I swap them or not, and then again he does the same process. So each time he has a probability of half of choosing the correct answer. So after n iterations, the probability of choosing a correct answer is n. When n is sufficiently large such that 1 by 2 is sufficiently small enough for his chance to be consistently right in order to guess the same, then I am convinced that he knows the information. So it is never perfect as always, but I can get as close as I can. Now we have two types of um, these zero knowledge proofs. So first is the iterative or the interactive. In the interactive ones, the prover, as we saw here, this was the interactive one. So first of all, I show two balls, then I again ask the response, then I again show them, then I again ask the response. So that's an interactive or an iterative one. So I have many iterations in, and it is interactive. So each time I ask a response from him. Other types are non-interactive or non-iterative. So in these types, I just, for example, we will see it in the later part. So for now, you can just see that that's only one way. So only one time, just one time, I show the info. I just ask for the information just one time, and then I am able to see if that information is correct or not. So first we have iterative schemes. For them we have these characteristics. For the mathematical complexity, it is more than non-iterative ones. Payload is also more, but for the statistical soundness, due to the many iterations that are done, they are generally more statistical sound than non-interactive ones, though we are not always sure. For the computing power, it is computationally light for the verifier but heavy for the prover. So the prover needs to do a lot of calculations, but the verifier has a comparatively light load. Now let's move on to the iterative schemes example, the Fiat-Shamir algorithm. So we have P and Q as primes and n equals to PQ is the multiplication of the two primes. We have already had that many times before. Now S is a another secret key chosen number. Now prover computes V equal to S square mod n, or it can be any other quadratic residue related to S. Then V is made public. The verifier needs to show that he knows S such that S square equals to V mod n. So this is the basic algorithm for the Fiat-Shamir iterative scheme. For non-iterative schemes, we have the following characteristics. So the mathematical complexity is comparatively lesser. Payload is also less because we have only one-time computation. They are less statistically sound though, and computing power is still, we have the computing power is not there much change there. The verifier needs a remarkably low computational power, but the prover, as usual, needs a lot of computation. Now we have the Fiat-Shamir heuristics. This is different from the Fiat-Shamir that we previously saw. This is a heuristics, or a kind of a not a proof based one, but a just a general idea. So as usual, we have the verifier sending challenges to prover to the prover and to the prover giving the answers back. But now, instead of the challenge, the verifier just computes the hash of some x, and this serves as the challenge for the prover. So the final proof consists of x and y. So E can be recomputed by the verifier, and so there is just a single proof that so he can such that he can verify x and y against E. Now let's look at some of the common examples of zero knowledge proofs. So first of them is the ZK snarks, or zero knowledge second non-interactive arguments of knowledge. So these are very short second, and have extremely fast verification in milliseconds or even in microseconds. Some examples are Pinocchio and Groth 16, and they are universal and updatable. So uh, we can change the algorithm for the same. Others are ZK stars. They are transparent, as you can see here, and they require no trusted setup. So instead of publicly verifiable randomness, they they require no such random element. So they are said to have post quantum security, or even after the advent of quantum technology, they are believed to be remaining secure. And the most importantly, they rely on hash functions. They are used in blockchains and quantum proofing. For bullet proofs, we have the major features as the again we have the transparency. Though they are little longer than ZK Starks, they have ZK Snarks. Sorry, Snarks are the fastest ones. They have a logarithmic proof size, that is, they are still compact, and many of them can be aggregated into a single proof. So an important term here is burdensome commitments. So for your information, we have for commitments are that if I have E equals h of x, so I store E such that E, once I have stored it, I cannot change it, but neither can the prover see it. So it is like uh, putting it into a lock and handing over the key to the prover, who cannot open it until he has the answer to the question. So here you can refer to them in a summary. Uh, some new frontiers for the same are post quantum ZPKs, the most important ones, and machine learning is also an important sector for development. We have applications in voting systems which need to be secure to avoid tampering. Then confidential transactions are also done using bulletproofs such as Monero. Uh, and so now we have the most important ones to the relatability of hash functions. So we have hiding and binding. Hiding refers to the fact that once I have uh, put the computed E, I cannot take back E or change E. Binding refers to the fact that even if I do not change E, I cannot tell the other verifier that the E that was in the digital locker type of was different than the one I had entered. This is guaranteed by the collision resistance of hash functions, which we had already seen, because they are it is difficult to find H and uh, such that both are equal to E. So uh, but still, we have some potential attacks and weaknesses that are not yet exploited, but maybe in the future. So we have violations of completeness, soundness, and that of zero knowledge. For more resources, you can refer this bibliography. So and I have used this calculator for the calculating the hash. That's it. Thank you. Hope you enjoyed this video.